Hello, good evening everyone. Welcome to the second video on circular motion and gravitation. So it's a long time that I had recorded the solutions for this. I had put forward this, I think January 6th or 7th, I think I did this video on questions, but unfortunately after this, I was not able to do it because there were lots of work at the school as well as at front home. And the moment I reached home, it was a bit late and I was not able to record it. Last week also I was quite busy. Today I found some time, so I thought, okay, let me do it. Anyways, I will somehow try to see to it that we do record the videos and put it across. Anyway, without wasting my time, let me give you the solutions. It's a long gap, and I hope many of you would have attempted the questions and got the solution so far and be eagerly waiting. And in the classroom also, we have finished this. Okay, now if you want to know about all the videos, you can go to this website. So all the videos are being put across in a proper way. And if you this will have videos apart from what we are doing here. Okay, and only for the homework videos, the videos are present in this portal. You can have a look at it also. Okay, now let us begin with it first. Okay, so a motorcyclist is cornering on a curved racetrack, which combination of this changes on the banking angle theta and the coefficient of friction mu between the tires and the road allow the motorcyclist to travel around the corner at greater speed. Now, this can be understood by writing a free body diagram correctly. Now, what we do is let us write the free body diagram. So the motorcyclist weight is acting downward like this. Then the normal force is acting like this. This is my normal force. So your mg cos theta, this will be my angle theta. So this will be my mg cos theta, mg cos theta. And then this will be my mg sin theta, mg sin theta. Now, if the person goes with a higher speed, okay, rather than the actual velocity, then what will happen? He will skid in this direction. So if he doesn't want to skid, then what should happen? The friction should be there. Now, because you have to avoid the slipping, you have to avoid the skidding. So if you want to avoid the skidding, where should the friction be? See, the person can skid in this direction. So you need to have a friction in this direction, right? So therefore, your frictional force should act like this. Now, let us draw the force equations. Since it's moving in a curve, what is the radius of the circle? This is my radius of the circle. So it's moving in a curve like this. It's moving in a curve like this, right? This is my radius of the circle. So therefore, now it should be like this. It should be like this on the other hand. Yeah. Okay. So let this radius be r. So in this case, now we see mg sin theta and frictional force both are acting along the plane downwards. Thus I can now write mg sin theta plus frictional force is equal to mv square divided by r. Now what is this frictional force? Let me write down here. Frictional force is equal to mu times m because sliding, right? What is n? N is nothing but mg cos theta. Thus frictional force is equal to mu times mg cos theta. Now let us write mg sin theta plus mu times mg cos theta is equal to mv square by r. Okay, or I will take this mg outside and then I will write this as sin theta plus mu cos theta is equal to v square divided by r. Of course, I'll cancel this m also. Cancel this m on both the sides. So therefore, you get this. This implies v square is equal to rg into sin theta plus mu cos theta. Mu cos theta. Right? Now you see, this v is directly proportional to theta. If theta increases, this term increases, but this term decreases. Right? Now, if mu increases, even this term will also increase. So therefore, both theta and mu should increase simultaneously. Okay? Fine. So the answer here is option A. Now let me go to the next example. Satellite X is in orbit around the Earth. A problem on gravitation. Satellite X is in orbit around the Earth. So this is the Earth. This is a satellite X. Satellite X is moving like this. Let the distance be R1. Okay. It's not given. Let me assume. Then this is X. I'll write X here. An identical satellite Y is in a higher orbit. An identical satellite Y is in a higher orbit. This is Y. This is R2. What is correct for the total energy and kinetic energy of the satellite Y compared with satellite X. See, the question is a bit twisted. Okay, you have to read this carefully. So he's given something, but look at the options here. Total energy of satellite X and kinetic energy of satellite X. It means be concerned of the energy of satellite X and the kinetic energy of satellite X. Compare it with the kinetic energy of satellite Y and total energy of satellite Y. Okay. So when you read this question, you will feel that you need to compare Y with X. But if you look at the options, it is X with Y. It's a reverse part of it. So you have to be very careful while answering this. Okay, so many of them, I have seen many of them making a mistake over here by not reading the question appropriately. Now towards it. Now, what is the orbital velocity of the satellite? We already know. What is that value? V0 is equal to square root of gm by r1. Now let me square this. V0 square is equal to gm by r1. Now, since it is something like this, can I write V0 square is proportional to 1 by R1, right? Because Gm is a constant. Whether it is there or doesn't matter, it is not there also doesn't matter. So it only depends upon your distance from the center of the to the satellite. Okay, G is constant, universal gravitational constant. M, mass of the Earth. It is not going to change for this satellite or this satellite because it is the mass of the Earth, right? V0 square is proportional to 1 by R1. Now let us find the kinetic energy of the satellite. Kinetic energy of the satellite, let me write KEX is equal to half mv0 square, which should be equal to half m v0 square is nothing but 1 by r1, or if you want to take the whole one, I'll take this also. Gm divided by r1. Or this should be Gmm divided by 2r1. If you don't want so much mathematics, you can directly say if v0 square is proportional to 1 by r1, then your kinetic energy x is also proportional to 1 by r1. You can write like this also, because nobody is asking you any math here. Okay, in a similar way, if you take up the total energy, now you see the particle is at this point. It has a larger kinetic energy. Okay, one is a little orbit. Now when it goes to this point, now let us consider this satellite. Now what's happening here? R2 is greater than R1. See, this distance is larger than this one. So what will happen to kinetic energy? Kinetic energy will still will be increasing or decreasing. See, R1 is this much. R2 is much larger, which means denominator is increasing. When denominator is increasing, kinetic energy will still decrease. Okay. Can we now say that kinetic energy of Y is still lesser than kinetic energy of X? Can we say this? Definitely you can say. Right? Kinetic energy of Y is less than kinetic energy of X. So it doesn't have much speed. It's going with much slower. Yeah, backbenches, right? That's what you can say. Satellite Y is at the backbench as compared to satellite X. Satellite X by a front bench. They're shouting like anything. But Y calmly is sitting. It's slowly moving there. Right? Now, what will be the potential energy of this? What is the potential energy? Potential energy is given by minus Gmm by R. Right? So here also it is proportional to 1 by R, which means potential energy also much lesser. So as a result of this, now what can happen over here? So this will have total energy. See, here it is negative, right? So total energy will still be negative, but it is bound to the Earth. Total energy of Y, okay, so is it is converted to it's given to kinetic energy. What we'll do is we'll write this as or maybe X only I will write. Total energy of X is equal to minus Gmm by R1 plus Gmm divided by 2R1. 2R1, right? So R, I have no space over here. I'll continue here, okay? Total energy of X is equal to, now you see minus Gmm by R1, I'll take this common by R1 into 1 minus, or maybe I'll take this plus here, Gmm by R1 into minus 1 plus half, which should now be equal to minus Gmm divided by 2R1. Now what do you see here? Total energy is equal to so much. Now you see, I have got kinetic energy equal to Gmm by 2R1, right? Here it is minus Gmm by 2R1. Can I write this as minus kinetic energy of X? Definitely right? So total energy is equal to negative of kinetic energy. Okay, that's what we have got. Okay, as a result of this, so when the particle is moving away, the kinetic energy reduces. But when you say negative of kinetic energy, the potential energy should increase. Okay, let me just give you an example. If I write numbers like 1, okay, let us say here the kinetic energy is 10 joules. When it goes here, let us say it is 5 joules. Okay. Now, if I ask you what is total energy, here this law follows. I have already told you according to this. Now, what is the total energy? Total energy according to this is, I'll write the same 10 joules, but I'll put minus 10 joules here. And here it is minus 5 joules over here. Now, which one is greater? Minus 5 or minus 10? Minus 5 is greater than minus 10. Okay. So, therefore, now what happens over here? So, when the particle, is at this point, the kinetic energy of the particle is larger over here. So, when I say larger, then these two answers are incorrect. So only these two answers are correct. Which one is correct over here? Now you see this has a much lesser total energy as compared to this, because it's near to the earth, it will definitely be bound to it. So therefore, this will have a smaller total energy and a larger kinetic energy. Okay. So do watch this solution once again if you do not understand, or you can write back to me so I can explain it completely. Okay. Now let me go on to the next one. The escape speed from a planet of radius r is v escape. The satellite orbits the planet at a distance r from the surface of the planet. Escape speed from a planet of radius r is v escape. Now you have a planet, okay, of radius r, is v escape. A satellite orbits the Earth at a distance r from the surface of the planet. Satellite orbits. This is my satellite, which is orbiting like this. So this distance is also r. Okay. What is the orbital speed of the Earth? You should write the orbital speed of the Earth in terms of the escape velocity. So towards it, what is orbital speed given by V0 is equal to square root of gm by r. When can I use this expression? Only when the satellite is revolving at a distance of r from the center of the circle. Now here from the center of the, is it from center of circle? No. See, from the center of circle, the distance of the satellite is 2r. So I will write this as square root of gm divided by 2r. Now, what is escape velocity for this particle? Escape velocity for the particle, for the satellite, when it is at the surface, is given by square root of 2gm by r. 2gm by r. This is r over here. It looks like a b. So therefore, now let us divide one by the other. V0 by v escape is equal to square root of gm divided by 2r multiplied by square root of r divided by 2gm. Okay, when I divide this. So this gm and this gm goes away, this r and this r goes away. So I am left out with 1 by 2 into 1 by 2 square root, which is 1 by 4, which should be equal to 1 by 2. So the answer is V orbital is equal to V escape divided by 2. So what is the answer? Option A. Right? So option A is the right answer. Okay, next, let us move on to the next one. The gravitational potential is V at a distance r from the surface of a spherical planet. Gravitational potential. This is spherical planet at a distance r from the surface of a spherical planet of radius r. With uniform density. Okay. At a distance r. Which means once again, at a distance r. This is the point P. At this point, the potential is V. Okay. What is the gravitational potential at a distance 2r from the surface of the planet? Now this is r. From the surface of the planet 2r should be this much large. What is the potential at this point? Let me call this as V2 over here. I want to find out. Okay. The potential due to the potential at the surface of the Earth is given by gm divided by r. Right? Now, if it is at a point P, now this formula is applicable only at this point. If it is at point P, Vp should now be equal to gm divided by 2r, because the distance from the center is 2r. Earlier, it was only r. At the surface, it is the formula. Vp equal to gm by 2r. Now, if I want to have V2 will now be equal to gm divided by this 2r plus r, which should be 3r, right? So, therefore, now what do I need? I need V2 in terms of V. That's it. So, let us write V2 by Vp is equal to what? V2 first, let me write down gm divided by 3r divided by gm divided by 2r, which should be gm by 3r into 2r by gm. This r and this r goes away, which should be 2/3. Thus, V2 should be equal to 2 times Vp divided by 3 or 2V by 3. So, the right answer is D. Okay. Then, Mass m is attached to one end of a string. Okay. The string is passed through a hollow tube and mass m is attached to the other end. Okay. Find friction between the tube and the string is negligible. Wow, no friction at all. No reality. Okay. Mass m travels at constant speed v in a horizontal circle of radius r. It moves like this. Okay. You keep on whirling like this, right? What is the mass m? Now, why should it move? Simple. Centripetal force. Where is the centripetal force acting? It is acting like this. Tension T should be equal to mv square by r. Now, let us draw the same thing over here. Now, if it is moving at uniform velocity, the tension is not changing. If tension is not changing, which means this is not moving downwards over here, right? So now what do we have here? The tension for this one is same. This tension is acting upwards. mg is acting downwards over here. Which m? Capital M. So thus, now here from the below object, for this one, the free body diagram tells you this should be equal to mg. Now we can equate these two. We can now say mg should be equal to mv square divided by r. R, what do we need here? Mass m. Capital M should be equal to mv square divided by capital M into r. Did we get it? Hey, no, sorry, capital M. R into G. mv square by r into G. Where is it? It's here. mv into G, mv square by gr. Okay. Now let us move on to the next one. A child stands on a rotating platform which is horizontal, that is moving at a constant angular speed. Constant angular speed. Okay. The centripetal force on child is provided by child is standing over here. Now, where is the centripetal force acting over here? So, centripetal force, let me do it. Yes, okay. Centripetal force is provided. When the child is standing over here, there are only two forces. If the platform is not rotating, one is normal force, other one is mg. Okay. Now, when the platform is rotating like this, now what can happen? Now, there's a centripetal force acting here. Is there a string or a wire or anything connected to him? No. Okay. So, because of centripetal force, the child can immediately fall here, right? But he is not falling. He is just standing there. Why is he standing? Because there's a frictional force acting over here, right? So, because of this friction force, the child does not fall. So, which is the right answer? The friction on the child's feet. Answer B. Okay. Let me move on to the next one. An object moves in a circle of constant radius. An object moves in a circle of constant radius. Let us read what kind of circle it is. Values of centripetal force F are measured for different values of angular velocity. Graph is plotted at omega on the x-axis. Which quantity plotted? Oh my god, I do not know what this one is. Okay. Let us assume it's a horizontal circle. Now, an object moves in a circle of constant radius. Constant radius. It's like this. Values of centripetal force. Directly Higgins law, which means the centripetal force is like this. Maybe this is a string. If this is a string, let me write T over here. The equation should now be equal to T equal to mv square by r. Values of centripetal force F are measured for different values of the angular velocity. Okay, now there is no T at all here. He says I can write this as T equal to F over here, where F is equal to mv square by r. F is equal to mv square by r. Now we know that V equal to r omega. I have not read the full question because he has said something about angular velocity. I'll substitute this as m r square omega square divided by r. This goes away. And thus I get mr omega square. Okay. A graph is plotted with omega on the x-axis. Omega on the x-axis. And then which quantity plotted on the y-axis will produce a straight line? So what should you plot so that you will get a straight line? Now, if you plot a graph of omega square versus f, we are not plotting it. Okay. So, if you plot a graph of omega square versus f, I can write omega square equal to 1 by mr into f. So, therefore, f will be your y coordinate and this will be your x coordinate. You can do something. But unfortunately, we are not doing it. Now, what we'll do is we'll take omega here. Omega is equal to 1 by square root of mr into root f. Now, if this is x, now what do I do here? I'll write root f is equal to root mr into omega. So I have already written as x here. Let me write this root mr by capital M. So this is y over here. Now what should be plotted on y? Root f. Right? So this should be root f. Simple. So that you get a straight line like this. What will be the slope look like? The slope will be equal to root of mr. Okay? Now let us move on to the next one. A mass at the end of a string is moving in a horizontal circle at constant speed. Okay, the string makes an angle theta with the vertical. What is the magnitude of the acceleration of the mass? Now, where is the acceleration acting? Acceleration is acting here. It's actually is acting here, right? We need to know that. So towards it, if T is a tension here. Now what do we have here? Now if this angle is theta, this angle should also be theta. So this should be T cos theta and this should be T sin theta. Now what we will do? We'll write T sin theta because you know it's acting along the radius. This should be equal to mv square divided by r. And then what is this is mass here? So mg is acting downwards. And then T cos theta is equal to mg. Now from here what I will do is, from here I'll find out the expression for T, which should be mg divided by cos theta. I take this value, substitute it over here. This should be mg sin theta divided by cos theta, right? And substitute this value should be equal to mv square by r. This m and this m goes away. Now what is it? What is it you need? You need acceleration of the mass. V square by r is nothing but acceleration, right? AC, centripetal acceleration, should now be equal to g into tan theta. Thus, acceleration is g tan theta. So this is the right answer. Hope you understand this. This v square by r. See this equation. I think many of you would have got confused. This mv square by r can also be written as m times AC, right? Where AC is the centripetal acceleration. Net force is m times E, right? Newton's second law. So you can write like this also. Okay. Let me move on to the next one. A bead is released from rest at point P and slides along a wire. Okay, you just leave it like this. There's no friction. It keeps on moving like this, goes around a circle and comes upwards. We is asking you what is the height h. No resistance, no air resistance, no friction. Okay, so when it comes upwards over here, its speed is 1.4. Now, how do we solve it? Simplest way is by using your work energy theorem. Okay, if you don't remember this, remember it like this. Delta P is equal to minus delta Ke. Delta PE is equal to minus delta Ke, or delta Ke is equal to minus delta P. Anything is fine. Now towards it, what is delta? Change. What is the initial potential energy? mgh. What is the final potential energy? See, this is the h over here, right? At this position, what is the final potential energy? Minus mg into 40 centimeters. See, I have started from here. mgh minus mg into 40 centimeters. 40 centimeters, 0.4. Should now be equal to minus. What is the initial kinetic energy? Kinetic energy, initial kinetic energy was 0. Minus. What is the final kinetic energy? Final kinetic energy is nothing but half m into 1.4 square. 1.4 square. Right? So therefore, now I have mg into h minus 0.4 is equal to, minus into minus becomes plus, which should be half m into 1.4 square. This is what I have. Now this m and this m goes away. Now if you solve this one, how much will this be? This will be 1.4 square is 1.96 divided by 2, and 1.4 square is 14 square is 196, right? 15 square is 225. That's right. Okay. So this will be, how much will this be? 2 9s are 18. And then you have, hey, did I put this mgh? Mg is here. Okay, fine. Okay, now what I will do is, I will not even do this much over here. So now let me write here. G into h minus 0.4 is equal to 1.96 divided by 2. H minus 0.4 is equal to 1.96 divided by 2g. Now 2g, what is 2g? 1.96 divided by, g is 9.8 once again. 2 into 9.8 is 19.6. So 1.96, 1s are 1.96, 10s are, right? Which should be equal to 1 by 10, which should be equal to 0.1. So h should be equal to 0.1 plus 0.4, which should be 0.5. So the answer is C. Okay. Last one. The change in the gravitational potential delta E of mass m is given by delta E equal to mg delta h. Which equation is necessary is important for the derivation for this expression. Now, how do we do it? So, now kinetic energy. Now, what we do is, if I want to, just a minute. Okay, so now, so here you see, as you see here, we need this mg delta h. How do we get this mg delta h? So what is happening here? So this is the, okay, this is the earth. So this is the particle. This is delta H. Okay. Now GP change through the surface is given by the equation. How do you know what is the GP? What is the gravitational potential energy? Simplest way. So what do? We find out what is the total energy here. E1, we'll find out what is the total energy E2 here. Then take the difference between them, right? So towards it, how do we do? At this point, what was the total energy? 0 plus 0, correct? No kinetic energy, no potential energy. Just a minute. I think my PPT got. Yeah. Okay. So now, okay. So what do we do here? So we say that, okay. So kinetic energy. So when moving through the height, delta H near the surface of the earth is given by it. Okay. So therefore, we use your conservation of energy, and we say that we need not even do this one here. We say that change in the potential energy is equal to negative change in the kinetic energy, right? So towards it, so change in potential energy. What was the potential energy at this point? 0. So first let us take the potential energy at this point, which is, so at this point, E2 minus E1, okay, should now be equal to K1 minus K2. Kinetic energy 1 minus kinetic energy 2. What is E2? mgh. What is E1? 0. Should be equal to, what is K1? At this point, it had some kinetic energy, otherwise you will not throw it, right? So half mv square. What is K2? It came to rest over here, minus 0. So therefore, now you see, this should be equal to half mv square. Thus, if you know this value, you can easily determine this, right? So therefore, this is needed as a part of the derivation. Change in potential energy should be equal to change in kinetic energy. Thus, the answer A is the correct one. These three are definitely incorrect. Okay, this gives you moment, which is of no use. Weight, no use. Work done. Work done. What is work done? Work done is power into time. Do we use any power here? Not necessary. Okay. Fine. So we have come to the end of all the 10 problems. And if you really like this video, do share and subscribe to my channel for more updates. And maybe by this Sunday, I think tomorrow also I may not be able to put across any videos. So by this Sunday, as much as possible, I would like to record and put it across. Thank you, friends, for being with me. Thank you once again.